Hi, good evening everyone. So let's start with the fifth session. So again, last day we got introduced to the neural networks, and so this for this week what we have in store for us is more interesting things. So how we process images, what kind of neural networks are proper for images and different kinds of data sets. So we are going into all of those directions. So because this is a computer vision course, our main focus will be on images rather than text, audio and other modalities. However, as we go forward in the course, we will also look at some basic architectures on how to handle these kind of different modalities. But for today we will start with some neural network architecture that is more suited to images than the ones that we saw last day. So let me share my screen. Right. So today's topic of discussion is CNNs, convolutional neural networks. So today's talk is organized in the following way. So since this convolutional neural networks, we said in the beginning that for handling images we need this special kind of network that kind of gives you the vibe that the neural network, the perceptron model that we saw last week, may not be very appropriate for dealing with something like images. So we will talk about why such models, the perceptron based neural network that we saw last day, why that is not suitable for handling images, and then we will talk about the basics of convolutional neural network. Praveen, I will give this a check. If it's not uploaded, so then I will make sure that they are there. So did you not find any of the notebooks? Because we surely uploaded them.
I checked in this particular thing, right? This lecture slides. In that link only we have to check, right? For weekday, week 2.
Okay, lecture slides you are able to access, notebooks not, right?
Lecture slide is taken to your link, and I'm able to see the PDF files, but
Okay,
no
okay.
collab.
Okay, got it. Fine, I'll just look into it after the class. Thanks for telling me.
Oh, okay.
Yeah. Okay, so we were talking about how this talk is going to be. So we'll talk about why CNNs are required, and then we'll go into the basics of CNNs, and then we'll try to understand what are the individual components of it and why they are useful, right? So without saying any more, let's begin with this. Okay, right. So let's begin with today's talk formally. So now coming to the interesting question of why the traditional neural networks may not work for images, right? So we all got a taste of what these neural networks look like in the last week's SIRS classes also, and in the TA sessions as well. We have seen what a perceptron model looks like, right? So it's like it's taking a data point as a vector, taking into consideration a data point as a vector, and then it learns weights to different, it's each of the vector components are connected to different neurons, right, through weight vectors, and these weights we are actually learning through some propagation method in order to understand, in order to learn the task at hand, which is very often like a supervised task where you are given a label and the model needs to predict, right? But somehow why is this so difficult in images, right? So the explanation is somewhat clear in this particular picture. So suppose this is an image of a cat. Okay, so what I do is, now first I take a small patch in this image, okay, and we all know that a color RGB image, what the dimensions are, they are h cross w cross 3, where h is the height, w is the width, and 3 is the number of channels. So suppose this image we have, and we are looking at the small patch, and we can see that even the small patch, which is very tiny part of the image, this consists of a matrix which is this huge, right? So this can be almost maybe what 15 cross 15 itself, right? So this matrix is a 15 cross 15 matrix, and this represents just this small part of the image, right? Now imagine if we take the entire image, how big that is going to be, right? So it might as well be like 10 to the power 6. Okay, so traditional images, I mean nowadays with with passing time we are dealing with images that are of, yeah, we are dealing with images that are 1024 cross 1024 cross 3, right? So such big high dimensional data. So imagine 1024 cross 1024, if you are vectorizing, if you are flattening the image into a vector, that becomes 10 to the power 6, right? So that's what I was talking about. And now those entire 10 to the power 6 dimensional vector, you have to pass through the entire neural network. So just try to imagine how many weights there are going to be, right? So that is why, like it says here, that images are very high dimensional data. So in the next slides we will also see some more visualizations as to the difficulties of making an image pass through a perceptron model network. But yeah, this is for your this is the intuitive explanation basically. So yeah, I mean this much data, this entire image, it's very difficult for the model to process it through a fully connected feed forward neural network, because its dimensions are, the models won't fit into the network. If we want such big models, if we want models to process this image as a vector, right? So now the question that comes is a fully connected neural network required at all? Now what do I mean by that? So given this image, what does a fully connected neural network do? It looks at at all the pixels of the image as a whole, right? So every neuron that is attached to this, suppose if we had flattened this image to a vector, we would have, suppose, and if we had neurons in the next layer, each of those neurons would be connected to every pixel in the image, right? Which is making this perceptron or feed forward neural network so difficult to handle. So question is, do we at all require so many connections, or can we do with smaller number of connections, right? So here, so what it says is whether it's enough to look at local spatial relationships or not. So what do I mean by that? So images, while they consist of many things at once, all those things are very local in nature, right? So for example, you can see that this is a cat, right? But you can see that its eyes are concentrated in this area, its nose is concentrated in this area, its ears are concentrated in this area. So to understand the catness of the cat, to understand that this animal is in fact a cat, you only need to understand that this may be the facial portion, right? So images, they are made of many local relationships that make up the entire story that is there in the image, right? So these are the legs, these two are the legs, this is the body, this is maybe some background, some house part, and so on. So all of these are very locally present. So you can see that this part of the image is not that related to this corner of the image, the ones that I am marking, right? These are not that related. So do we need to look at the entire image at once, or is it enough to look at small regions in the image, local regions, small regions in the image, and it's enough for the model to learn what is going on, right? So this is what we have to focus on, right? So we have to make use of this special property of images, where I wouldn't say property, but yeah, I mean this happens in an image, that important parts in the image are concentrated locally, right? So can we take advantage of this observation and make changes to the neural networks, right? That is what we want to see. So an explanation, a visualization of what is going wrong with the current feed forward neural network. So FFNN stands for feed forward neural network. So imagine this, so take this picture of Einstein, and suppose at this point let the image be very small, okay, and let it be 200 cross 200. So that's what I'm saying, even a 200 cross 200 image is not that large. So 200 cross 200 image means what? So there are 40k pixels, right? 40,000 pixels. Now suppose you have, so this is the first neuron, this is the second, third, and so on. Okay, so the first neuron itself needs 40k, 40,000 hidden units, right? And now, so generally when we draw neural networks on paper, we only draw suppose 3 layers, 3 neurons or 4 neurons in every layer, right? But when you have 40k, 40,000 connections or 40,000 input points, so if we had vectorized this image, our vector size would have been 40,000. So when you have 40,000 input elements or input components, 3 neurons here won't be enough, right? So you need many more neurons to be present here. Okay, so generally the norm is that whatever is your input size, your number of neurons here should be proportional to that. Okay, so that means another 40k here, right? So because you have a 40k dimensional input here, so number of neurons here also you can take it to be 40k. So now one neuron has 40k connections, all other 40k neurons, you can imagine 40k into, that is like 40k square, 2 billion, okay, close to 2 billion. So just having one layer in the neural network, just one layer, that gives you 2 billion parameters, right? So that is something which is impossible. So next, in the next layer, you will again have something proportional to 40k hidden units, maybe 20k, even 10k. So even if 10k is there, then again you can imagine how many connections we would need, right? So this is what is called parameter explosion, right? So if you try to process something like this, and in fact you can go ahead and do this as well, take a 200 cross 200 image and just try to train a maybe 2 layer 3 layer neural network on it, and you will see what happens. So this basically freezes the GPUs that we have, the resources that we have. Our resources cannot fit so much, right? And this leads to some sort of an explosion, your computer crashes, right? So also, so again, like I said, that do I need to look at this entire Einstein's image to understand what is going on? So as far as the computer is concerned, this is the picture of a person, right? Is the entire picture containing the person? Yeah, maybe in some sense you can say that 80% of the picture contains Einstein, but most of Einstein's features are concentrated in very, very small areas. So eyes here, nose, mouth, hair. So this is what I mean by spatial correlation or spatial local spatial relationships that is mentioned here. So this is what I mean by that. So I do not need to look at the entire image at a go to understand the smaller features like eyes, nose, hair, and so on. So it's okay if I look at even smaller parts, right? And they are all concentrated locally in some area, in some small area, right? So can we take advantage of this? That is the question. Next, obviously waste of resources. We do not have enough resources to train these kind of models. So even trying to do that is leading to some sort of waste, right? So 2 billion parameters in a single layer, it's impossible for us to handle, right? So we cannot do it. Thirdly, another problem is that we do not, so since we have like 40k connections here, another 40k connections with respect to this neuron and so on. So with so many parameters, do we have enough data to train? That's another question, right? So this is, I mean, this many parameters and very less amount of data to train. So not very less. What I mean by this is that we have data to train, but those data, whatever we have, they may not be suitable for training this entire huge chunk of network, right? So this big network cannot be trained by whatever data we have, right? So remember this, that the larger the model, you need more and more and more data to train it. So how will you have so much data that can train this larger model which has 2 billion parameters in a single layer, right? So this is what the problem with feed forward neural network is, and hence we need to move on from feed forward neural networks and introduce something a little bit more sophisticated that takes advantage of this fact, right, that the spatial correlation is local. The but the important features in the image are actually located in small buckets, small sort of pockets in the image. So how can we take advantage of that? That is what CNN is about, right? So coming to CNNs, it looks at local regions, like we said. Okay, so suppose this is an input image. Okay, so this is a teddy bear which is reading a book. Now what we do is, instead of looking at this entire image, instead we look at it patch wise. Okay, so we look at a small region of it. Okay, and this region, what do I mean by looking? So basically whatever you saw here, 40k connections, instead of having all those 40k connections, we'll only have connections that can handle this much data. Okay, and we'll not fit it into a feed forward neural network. So we'll have so again we'll go into more details in the next slides, and also sir has already explained, but we'll look at this region and we'll have some parameters that are only of this size, of this dimension. Okay, so this, the number of parameters are proportional to this patch size, and these parameters that you have, they will be shared across the entire image. Okay, so that was not happening before, right? So here you can see that the neurons that are present here, so all these connections are only meant for this neuron 1. Neuron 2 will have its own set of connections, neuron 3 will have its own set of connections. Here instead what we are doing is, we are saying that we will have a set of parameters, but these parameters will be shared by all the, through the entire image. Okay, and this parameter, so once we so what we basically do is, we take this small patch, right, we learn the parameters, and the next neuron that we have is something like this. Okay, so that basically it represents this small area of the image. So or so yeah, something like that. So again, some even more better intuitive explanations will be provided in the next slides, but the point is over here that this part, this is a neuron, okay, which is looking at only this part of the image. Previously what we were doing, we had a neuron like this which was looking at the entire image. Here we have a neuron which is only looking at this small part of the image, right? This is another neuron which is looking at even a suppose this part of the image. Okay, so you can see that each of the neurons, they are basically nothing but they are looking at different sections of the image, where the this patch that we have is equal in length. Okay, so again we'll go into the in the next slides, it will be much more clearer what I mean by what I mean by the parameters, how they are learnt, etc. But just take this to be a neural network, right? And again, how the neural network is created, that is coming up in the next slides. But this is the input and this is the neuron. So the input and the neuron are connected in this way. So if this is the final neuron, this is the input part that you look at. So a small region in the image. So this is what we look at mean by looking at local regions. Okay, so this is how you use convolutions for this. So you learn parameters. So what the parameters signify is something very intuitive basically. So the parameters that you are trying to learn, so we will show in the next slides again, but I am telling you anyway that whatever parameters we learn in this particular neural network, those are not like learning meaningless weights. Okay, so since they are looking at local regions, so all of these parameters basically, some parameters are meant for just looking for eye sort of image, eye sort of structures. Some parameters want to look at nose sort of structures and so on. Okay, so suppose I have a parameter here in this neural network which wants to detect, which is meant for detecting feet, right? So now what we will do is, we will look at the entire image window by window, like we used to do convolution or correlation. So we will look at the different patches of the image, and suppose when we arrive here, so because this is the feet of the teddy bear, and our the parameters that we had used, they were also meant for looking at the feet. This is the area for which the corresponding area here will have the maximum value. Okay, so this part which contains all the neurons this is called the activation map, right? So again things will be a little bit clearer in the next slides, but this is the main concept here is that there is a, first of all, we save a lot of parameters because we are looking at small parts of the image, and this parameter, this feet parameter that I talked about, so this parameter, whatever size it is, so we will talk about that in the next slide, but this parameter is shared across the entire image, right? So it's not that, so while this neuron was looking at all the different pixels, this part, whatever parameters we are learning here, it's looking at different parts of the image separately, which makes the number of learnable weights much smaller than what we see in the feed forward neural network. So now in the next step, so again we'll elaborate on these in the next slides, but still a little bit of introduction. So next, once we do this convolution, what we do is, so even after convolution the number of neurons is not very small, okay, that we'll see. So number of neurons is not very small, and it still is, we are still unable to feed it into some traditional neural network, it's so large, right? So that is why what we do is some sort of downsampling called pooling. So pooling downsamples the number of neurons that you have here and retains only either, you know, some very important information or some aggregate information that it captures from the previous convolution layers. And now once pooling, so pooling, as I said, is downsampling, right? So it has reduced your number of neurons to a large extent by preserving only the important or aggregate information from the previous layers. So once you are able to do that, and once you have, so you basically end up with number of neurons which are okay to be fit in, okay, to fit in the GPU, okay. So once the number of neurons are less enough, low enough to fit into the GPU, you connect them to a fully connected neural network, and then like we showed last time, from the fully connected neural network you have one or two such layers, hidden layers, and then you basically produce the output, okay. So maybe here we are just trying to predict what animal is there in the image, right? Here the answer is going to be teddy bear. So your fully connected network is the one that is going to predict what is the correct output for, or what is the prediction for this particular image, right? So this was just a sort of an introduction. I know maybe it's a little bit hand wavy at this point, like what is going on. So that's why after this introduction we thought of keeping the individual detailed parts of the CNNs in the subsequent slides. So the most important part is the convolution operation, okay. So what you do here is, as I said, like I said, so this part, so this is the part of the image that you are looking at, okay. So in order to look at this image, so you need some learnable parameters to understand what is going on in this small patch, right? So in order to do that, your learnable parameters that you have, that is like a matrix of the same size as this patch, okay. So it's like you have this small matrix like 3 cross 3. Suppose my image is a lot simpler than what we saw last time, it's a 6 cross 6 image, okay. And what we are trying to do is, our patch size, the local patch size that we have here, that is suppose 3 cross 3, okay. So what if the patch size is thought of as 3 cross 3, our number of parameters or our parameter matrix will also contain 3 cross 3 elements, okay. And now what we will do is, like I said, and just follow this GIF. So we have this parameter matrix, this which we call, by the way, which we call kernels or filters. So this filter we have. Now what we will do is, we will simply put it over this particular 3 cross 3 window, and we will do a dot product, okay. We will get a value, and this will put here in the first position. Then we will take the second window, we will do a dot product with this particular matrix once again, the filter once again, and this will put in the second position, and this will continue, okay, until all the positions are filled. So just see here that if you have a filter like this and a window of the same size, what you get in the output is a scalar, okay. Now how, okay, so what do these scalars signify? So scalar, by scalar I mean these individual cells. Okay, these are individual numbers that we get, because we are simply doing a dot product. By dot product, actually dot product is not the correct term to use, it's a element wise product that we are doing, and the sum, right. So this with, so when our first window is this one, the first 3 cross 3 matrix, this with this we are multiplying, this with this we are multiplying, and so on. So once the products are there, we take a sum of them, and that gives you one number, and that is what we place here. For the next window, we place in the next consecutive place, and so on, until the entire thing is filled, and this becomes our, so all of these, this 4 cross 4 matrix that we get in the end, this is called an activation map. So this is the image, this is the filter, this is the activation map. So this activation map, what we are doing, this activation map is basically the output neurons that we get after convolving with this image and this filter. So again, like I said, note that this filter, we are moving across the entire image, right. So this is being shared by the entire image, right. So this, the 4 cross 4 matrix that you are seeing, so this has 16 elements, right. So these 16 elements are the 16 neurons that you get at the end of the convolution operation. So what this signifies is something like this, that suppose this, obviously this filter is something that we want to learn, okay, and how do we learn it? So again, going back to this model, this architecture, so we do the convolution with learnable weights, right. Maybe we repeat this convolution layer multiple times, then we do pooling. We will come to pooling in a bit for those who do not recollect, and then we pass it through to a fully connected neural network. Now, like I said, the fully connected neural network will basically finally lead to some sort of prediction. Okay, so suppose you have a teddy bear here, so maybe the neural network predicts it to be something else like a dog. Okay, so based on the predictions of the neural network, we will calculate the loss function and we will back propagate through the network. Now this back propagation through the network will basically train the model to learn the correct weights, okay, in the filters. So once you train the model through back propagation, this is the, these weights will be learnt automatically. So the model will automatically figure out what values to put here so that it understands the image maximally. Okay, so based on that, so here basically finally if you look at if you go and study, you will see that these features, these parameters that are there, which we are calling filters or kernels, these are not random numbers. Okay, so these are like meaningful small matrices which kind of look for some meaningful semantic region in the image. Like for example, I was talking about the feet, so that this small kernel that you see, it might look at properties in the image that are looking for feet. Okay, so if it finds something like a foot in the image, the corresponding value here is going to be very high. That's how you know that so if you for example see very high values here in the matrix, you will know that okay, this is where in the corresponding part of the image, this is where we had seen some feature that the neural network was looking for, that the kernel was looking for. So for example, in the example I gave, it can be feet. So if the kernel is moving around here in this region, since it sees a feet, this part of the final of the activation map will have a very high value. So that is how the filters start to make sense once they are trained properly, and this is the nutshell of the convolution operation. So this is very simple, just nothing for non-electrical guys. So this is nothing but element wise product and then sum, and that product, that sum of products, you put it in the individual cells and these become your values. Higher the value, the more the filter and the individual patch in the image has matched. That is what it signifies. Okay, so a little bit more realistic, coming to a little bit more realistic scenario now. So suppose like there are many data sets that we have, they are all 32 cross 32 cross 3 images. So 3 signifies that the images are color images, so 3 channels. So 32 is the height, again 32 is the width, and depth is 3, or number of channels is 3. So these slides are from the very popular CS231N course in Stanford, so you people can refer it if you want. So suppose I have this image, and now what I want is I want to learn a 5x5 filter. Okay, so what size filter you want is up to you. So that is what we call a hyperparameter. So the size of the filters, forget about this 3 now, this 5x5, this is up to you. Generally the general norm is to have it, the most common filters are of size 3x3, 5x5 or 7x7. So it's a norm to keep them to be of these sizes, right? So you can understand that this size actually also defines the patch in the image that you are going to look at, right? With a 5x5 filter, you can only look at a 5x5 window in the image in order to do the convolution operation, right? So now what is this 3 for? Okay, so remember that in this 5x5, this patch in the image is only across the height and the width. Okay, but you have to remember that there are 3 channels as well. So if you want to do a convolution operation properly, right, so just having a 5x5 matrix is not enough, just having a 5x5 filter is not enough. What you need is to cover the third dimension as well. So you need a filter which is like this, so it will cover this entire thing, okay, this entire thing in the third dimension also. So that is why always follow this, that whatever is your input images number of channels, that can be 3, suppose it is 10,000, okay, even then your filter size will be 5x5 cross 10,000. So this and this, they should match, okay. This, the first two, they are up to you, okay. If you want, you can even choose a 50x50 for example, but this 50x50 is up to you, this is not up to you, this depends on the input, okay. So this is the general size of a filter that we wanted to explain, and why this 3 is required, that you have to understand and remember for the rest of your life, that this is always fixed to be the depth that you see here, okay. Now what is the norm again, going back to the previous slide. So I'll take the first window, then I'll slide to the next window, then I'll slide to the next window, and this is how I'll go on. So that is what it says, that convolve the filter okay. Yeah, so that is what it says, that convolve the filter with the image and slide it over spatially, okay, and computing dot products, right. So this is what I exactly say, that the first filter is like this, it takes the first 5x5 patch in the image, taking the entire 3 dimensions, I mean 3 channels, then you slide by 1 and then you take the next 5x5, and this you keep on doing, okay, until you reach the end of the image. That is the entire convolution like operation, that is as simple as is, right. So this is the simple convolution operation that we use to learn the parameters, okay. So this is the parameter that we want to learn, right. So this we are passing over the entire image, right, and yeah, I mean the moral of the story is that this is how the filter size should be. So these are very small details, but these are important concepts to be able to grasp, okay. The next thing is that, so you have this 32x32x3 image, and you have this 5x5x3 filter. So we have established, I hope, that this 3, why it is 3 here, why not something else, but let's accept it for now, and we have a 5x5x3 filter. So now, given this particular patch in the image, what is the okay, so what are we gaining out of it? So like again going back to this GIF, like I was saying, that the moment you have this filter and you pass it on to some window in the image, all you are getting is a sum of products, which means you are getting a number which is corresponding to this cell, the first cell, right. Okay, so that is what it exactly says, that the moment you convolve an image, some image patch with the filter W, what you get is one number. Okay, so what it says is the So this one number is the result of taking a dot product between the filter and a small 5 cross 3 chunk of the image. So how many how many computations do we have here? So we have a 5 cross 5 cross 3 equal to 75 dimensional dot product, because these are the number of times we are multiplying, right? So this is the number of multiplications, and we have to add a bias as well. Okay, so that is what so one addition and 75 dot multiplications, right? That is the operation that is required. So like practice these things a little bit, because questions are asked on these things, and they might be a little bit confusing on sometimes if you are not very used to this, right? So the whole operation is very similar to W transpose X. So W transpose X, what you do is W1 times X1 plus W2 times X2 and so on. So the entire operation is exactly same as that, and plus you add a bias. So you get one number out of it with these many computations, mathematical computations, right? So now you get one number out of this particular patch in the image. Now if you do this computation across the entire image, what you get? So for the first window here on this top left corner, you get one number, then you slide by one position and you get one number, and so on, right? So what you get is again a series of numbers, okay, like a matrix of numbers, like we saw here. Okay, if we forget about the channel for now, so what we get is a matrix of different numbers, where each of these correspond to the some patch in the image and the dot product of that patch with the filter that you want to learn, right? So this matrix, so again we look at why the size is 28 cross 28, but hopefully you can figure out by now why the size is this way. But this image, because so this particular matrix that we get is of size 28 cross 28, and because we are getting a single number out of this computation, so this is basically like a single channel image. Okay, so we have a 28 cross 28 matrix basically, because there is so because it's 28 cross 28, we can just say 28 cross 28 cross 1, right? It's like a image with one channel. Okay, so this is what we get, and this is what is known as the activation map. Okay, so this is like the output of this convolution operation, where individual elements in this activation map are nothing but the neurons that are obtained by convolving the weight vector with the specific area in the image. Okay, so this why am I suddenly expanding this channel from so I could have easily said that this is 28 cross 28. Why this cross 1 as well? So we'll get to know about this shortly. So basically this, in this particular slide, what we did was we convolved using one filter. Okay, but it may not be enough to learn just one filter, right? So the story I gave you in this teddy bear image, that suppose one filter that we are trying to learn only understands feet. So these filters, what we want them to learn is small parts, small particles, or small parts of certain entities, like maybe nose, eyes, maybe some, if you think of a card, then maybe it's one patch can be a door handle, something like that, right? So they are just, what we want them to learn is simple components of the different entities that we see around us, right? So yeah, so that's why if we have only one filter, suppose in the teddy bear case, we can only learn maybe what are the feet, where are the feet of the teddy bear, but is the feet enough? No, right? So we need to understand the other parts, the face, the nose, the eyes, the body, and so on. So we need all those, right? So in order to incorporate all those, we need different filters, right? So one filter will hopefully learn the feet, one filter will hopefully learn the hands, maybe one filter will hopefully learn the eyes, and so on. So we need multiple filters in order to understand the different components of different entities that we see around us. So suppose now I have another filter. So previously I had this blue colored filter, now I have a green colored filter. So I do the same convolution operation on this. This is again another set of weights. So this is another matrix of weights having dimension 5 cross 5 cross 3. Okay. So again suppose we, so this is a different set of weights, this is just another matrix after this, right. So again we convolve the entire image with this particular filter, and what we get is again another 28 cross 28 cross 1 image. Okay. This is the second activation map after the blue activation map, right. So now instead of having 2 filters, suppose we have 6 filters. Okay. So in order to learn different things, so again how many filters you want to have, it's up to you. Okay. So now the important thing to note here is that with the 6 filters, here we get 6 28 cross 28 images, right, 28 cross 28 cross 1. So now if we stack them together, this becomes a matrix of dimension 28 cross 28 cross 6. Hence I introduce the third dimension in the activation map. So whatever number of filters you have, suppose number of filters is n, right. So that becomes your channel number for the activation maps. So again this is very important to remember. So these are stacked up to get a new image of size 28 cross 28 cross 6. So how this 28 came, we'll look into that, but it's fairly easy to understand, but this 6 part is pretty important. So this is a fundamental understanding that you that you should have about CNNs. So initially we had started with 3 channels, right. We ended up with 6 channels because we had used 6 filters. So the output number of channels is equal to the number of filters that we had used. Okay. So you will get questions in future also, and in the maybe in the exams also you will get similar questions like this. So these are areas to focus on, like what are the filter dimensions, what is the third dimension of a particular filter, which is equal to the input dimension, input third dimension. Okay. And what is the output dimension? It is basically the number of filters that we are using. Okay. So now just remember that we had this 28 cross 28 cross 6. Now suppose we are doing another convolution. Okay. We are doing it another time, and we have 5 cross 5 filters, again the same size. So now my input is no longer this, my input is this, right. So that is why even though we need a 5 cross 5 convolution filter, if we want the filter size to be 5 cross 5, what is going to be the third dimension? It is once again going to be same as the input, right. So here input is 6, that is why we need 6 here on the third dimension. So our filter dimension will be 5 cross 5 cross 6. So this 5 cross 5, this one and this one, these are in our control. Okay. This 6 here at this point, this is in our control, but this is not, this third dimension 6 is not. Similarly here we are saying that suppose we will have 10 filters. Okay. This 10 is in our control, and because of this operation, what we end up is with a slightly smaller matrix of size 24 cross 24. The number of channels now becomes equal to this. Okay. So now in the next time if we do decide to do even another maybe 5 cross 5 convolution, then the number of channels, the third dimension in that convolution filter is going to be 10. That is going to be fixed, that is going to be dependent on this. This one is a hyperparameter, but this one is not, right. And then again you can choose the number of filters that you want to have in the next layer, and that becomes the channel size of the next activation map, and this goes on and goes on. Okay. So now one thing that you can see is that in this way, so we had started with a 32 cross 32 cross 6 image. So 32 cross 32 cross 3 image. Now forget about the channel dimension for now. So in the next, once we do one set of convolution operations, we have a 28 cross 28 image. In the next step we have 24 cross 24. Okay. So just keep a note of this fact that the number of the dimensions of the activation maps are actually reducing, and this is something that we want. Okay. The larger the image that we have here, the more difficult it is going to be to use a feed forward neural network on. So for using our final results are going to come from a feed forward neural network, the final prediction, but in order to be able to use that, we need the dimensions here to be small enough, right, so that we can have all those connections that we saw in the Einstein image, right. So a little bit more visualization. Okay, so what is, so here in the title we see two terms, stride and zero padding, right. So what is stride and what is zero padding? So stride basically is something like, so this is the first window, right. So this is a 7x7, this, imagine this to be the image, and we have a 3x3 kernel. So for computing the dot product, we take the first window, right. Now in the previous descriptions, how did I say? I said that after the dot product with the first window, you do the dot product with the second window, then you do the dot product with the third window, and so on. This you continue till the end. Okay, so this is called stride 1 convolution. So you are moving from this particular part as the starting point of the window to this. Okay, so this 3x3 window is the next one that you take. Then again you move by 1 and you go to this, from here to here. So you take this one. Okay, now you can vary this. Okay, so that is why this variable stride comes into existence. Okay, so you can even put stride to be 2. What do I do there? Very easy. So I start this is the window that I always start with. Now instead of moving to the next one, I leave this one out, I put a gap of 1 and I take 2 steps and I go here. So my next window starts with this. Okay, no longer I am taking this one that I am pointing. Instead I am directly going here. Now again instead of taking the, so I am here at this point, instead of taking the next one, I again take 2 steps and I go to this one, means I will take this window. Okay, so this I will repeat throughout. So that is called stride equal to 2. So very often strides with more than stride equal to some quantity, generally 2 is the highest that I have seen, but stride equal to 2 is also something very common. So one thing you have to realize as well, that when you have stride equal to 2 suppose, then you have this, so like I said, you keep a gap, so you take 2 steps to take the next window. So you know, once you do that, convince yourselves with this fact that your activation map size reduces even further. So this is another way of downsampling the image, right. So initially you are having, suppose a 5x, your activation map was 5x5, now it is becoming just 3x3 with your stride equal to 2. So you are losing some values, but you are downsampling your image further, right. So this also is something that is very common. Now suppose I want to do stride equal to 3, right. So here, I mean, we have a problem. Okay, so let's see why. So stride equal to 1 means, we all know that we take the first window, then this is the second window we take, and so on. Stride equal to 2 means, again we take this is the second window that we take. What is stride equal to 3? Instead of taking 2 steps, we take 3. So here we go, this is the first window, next window is this one, this. Okay, so this is my next point where I am currently located. Now I have to take again a jump of 3, so I reach here. So this is my starting point. Is there anything in this side? Nothing, right. So this is where I am at this point, and I need a 3x3 window on the right. Okay, but nothing is there. So that is what is called, that means what, that with stride equal to 3, this whole convolution process breaks, because you are not able to move towards this side. Yeah. So because you are unable to move, towards this side. So that is why you cannot set just any stride. You have to set a stride which matches with the size of the image, and we will see shortly like what is a good starting point, like what is a good value for stride. But suppose so we already saw like what stride equal to 3 is doing. Okay, so how to solve this problem? We can use something called zero padding, which we will see in the next slide. Okay, so we can do, we can like operate with any stride value, but then we have to make sure that we are not making a mistake, we are not coming out of the image, right? So if you do that, if in your code you set stride to be something which is not proportional to your image size, then your code should throw an error. So if you go to PyTorch, it will throw an error if your image size and your stride, they do not match. Okay, so one thing that you can understand from all these, and obviously it's written here also, that this whenever you do convolution with a certain image size and certain filter size, the output, the activation maps dimensions are not random. Okay, they can be mathematically formulated, and this is exactly the formula for that. Okay, so this is something that either you should remember or it should come to you automatically. So n here is 7, which is the image's dimension. F here is maybe the stride, F is the, my bad, F is the filter size, and divided by stride plus 1. This is your output activation maps dimensions. Okay, so you already know the third dimension, it's just the height and width that we are talking about. Okay, so for example, n equal to 7, f equal to 3. So now you know like why we were, if you put the, so we had started with 32 cross 32, why we went into 28 and 24, now you will be able to grasp. So you have to remember this formula. So for example, in this case, if we have a filter size of 3 and stride of 1, sorry, so then if you put in the formula, it's 7 minus 3, 4 by 1, because stride equal to 1, plus 1 equal to 5. That is why we were getting a 5 cross 5 matrix. If stride is equal to 2, like I said, we are going to get a 3 cross 3 matrix. And the moment you have stride equal to 3, you can see that we are not getting an integer. So basically your n is not in your hands, f is in your hands, stride is in your hands. So you have to make sure that at the output you are getting an integer for sure. No fractions will do here. Okay, if you get a fraction, your code throws an error basically. But there are also, suppose you have a certain image size, you have a certain filter size, and you have a certain stride, and you like them too much. Okay, you do not want to change them just because they are not coming into a integer. So what do? You do this zero padding. So notice this, that here, notice this, that this 2.33 could be very easily avoided if we had changed the image size a little bit. Okay, the filter size, it's not really very practical to change, but the image size could be transformed a little bit so that this could be fit, right? For example, what can I do here to make this divisible by 3? So for example, 7 minus 3 is 4, right? So 4 by 3 is not divisible. So suppose if we had made this 9 minus 3, 9 minus 3 is 6, 6 by 3 is 2, 2 plus 1 is 3, so this becomes an integer, right? So if we could make this 7 equal to 9, if we could change this image from a 7 cross 7 image to a 9 cross 9 image, we could have saved our day, right? And that is exactly what we do in padding. So we have a 7 cross, this white part, this is our original 7 cross 7 image. Okay, what we do is we add a layer of zeros on top, on right, on left, and on top, right, below and left. Okay, like this. So it's just like a square you are adding around the image, or a rectangle you are adding around the image. Okay, so this is called padding, where you simply put zeros in these gray parts, and this white part is your original image. So if you have an image like this, so this becomes, because you are adding one 0 on the top and on the bottom, on the left and on the right, your final image dimension becomes whatever is n here plus 2. Okay, so we call this padding with 1 pixel border. So in every corner we are adding 1 pixel border. Okay, here 1 pixel border you can see, here 1 pixel border, here 1 pixel border, here 1. We could even add another layer, okay, like this. Okay, that would have made it 2 pixel border. Okay, so that means what, that on this is our this white thing is our image, right? So on top of this we are adding 2 more basically cells, 2 more pixels, okay, on top, and 2 more pixels on the left, 2 more pixels on the right, and so on. So whenever your number of, so whatever your pixel border is, so here 1 pixel border, your image size becomes 2 into that. Okay, so let's call this quantity, let's which is 1 here, we can call it as capital P, right? So your output image, so your transformed image will have a size of n plus 2p. Okay, 2 because on all sides you are adding, okay, you are adding 1 pixel on all side. So because you are adding on left and right both, you are adding 2 pixels actually. So that is why instead of 7 cross 7 you get a 9 cross 9 image. Okay, so it's basically n plus 2p, that is what your image dimension becomes. They get something? Sure. Oh, sorry, I got a message. Okay. Praveen, no, kernel is kernel. Okay, let me, sorry, I missed all these messages. So kernel like Gaussian filter, no, Gaussian filter is fixed. Okay, that you have to understand. So in image processing we use kernel, so the concept is very similar. So we use kernels in a similar way, we convolve with the image and we get outputs out of that. But here in the Gaussian kernel, you know what the kernel values are going to be. Here it's just randomly initialized and you are using backpropagation to learn what the values should be. Okay, so deep learning is all about, you want to learn certain things, you just initialize them as random and then you use backpropagation and fill the correct values into the filter. So what the filters, these small these small filters that we are seeing here, they are initially randomly initialized, they are not Gaussian kernels or anything. Okay, and by the way, Gaussian kernels and all, they are designed to change the image in some way, right? So here these kernels, so functionally also they are a little bit different, so they are not changing your image in any way. What they are what they are only doing is they are trying to find certain features from your image, right? So here, like I said, that it's not trying to blur the image or it's not trying to sharpen the image or anything, it's trying to find what are the important parts of the image, like the feet, the nose, the eyes, and so on. So in this way it's different from Gaussian kernels. So the concept of convolution is still the same, but the kernels are entirely learned by the network. So that's your first question. Yeah, stride I'll explain. Sorry for missing the messages. Yeah, okay, yeah, we were here, right? So yeah, so by stride what I meant was this. So you can, this window is already put here, right, on the first patch, first 3x3 patch. What I am saying is, when I move, so I wish I had a matrix with written numbers, that would have been easier, but okay, is this a little bit better? No, I think this will do whatever I was showing. So generally what you do is, you in the next part, so even when you do other forms of convolution, once you are done with this window, you move to the next window, the one that I am bordering. Okay, this is what you do normally. In the next step you move to this window and so on. So very slowly I am trying to mark the windows. So this is like going one step at a time. By stride, what I mean, when you have a stride which is greater than 1, what do I mean by that? That once I operate on this green window, my next step is not to go into this immediate window, immediate next patch. Okay, what I will do is, so when I am in this green patch, my actual location is this particular cell. Okay, this particular component in the matrix, in the image matrix. Now what I will do is, I'll move, so I need to move towards the right, right? So instead of moving immediately to the next one and start the window from there, what I'll do is, if stride is equal to 2, I'll move 2 steps from here. So I'll take a jump, I was here, I'll take a jump 1, 2. So this becomes my, this cell is my current location now. So the window around this cell, that becomes my starting point. Okay. Now again, so in the next part, next step what I do, so I am in this cell. Okay. Now I'll again take a jump of 2. So 1, 2. So now I am in this cell. Okay. So now I'll take the window around it in this way, right, and I'll do the convolution. So that is how, so you have now moved entirely towards the right. Now you need to move towards the towards downside, right? So what you do is you again come back here. Okay, come back to your initial stage. Now what I have said, normally what would you have done? Normally you would have gone from this cell to this cell and started your window from here, this particular window. Okay. But what I am saying you need to have a stride of 2. So now again when you are moving below also, then also you need to have a jump of 2. So I jump from here and then here. So this is the second jump and this is the cell that I am currently at. So I will take this window for convolution. So all these windows that I did not touch, so this second window for example, these are not taken into account. Okay, this second window that I am trying to mark, these are not taken into account, these values are not computed at all. So I'll only compute the values that I'll only take the patches that I'll reach with my jump equal to the stride value, right? So this is the next step. Okay, and then again from here I'll move here and then I'll move here and so on. Again I'll when I go towards the down, from here I'll go to this, then this, then this. This is how I'll do. Okay, so what I suggest you to do is, based on whatever you have understood, so why not take this 7 cross 7 matrix, fill it up with something, right? And suppose you have another 3 cross 3 matrix of some random values, why not just perform this on your own, on your pen and paper? So then you will understand what stride would mean. So all I am saying is, take this window, right, take this first window and take a jump 2 steps. So next time your starting point is this cell, then the next point your starting point is this cell, and so on. So yeah, so also, so if you go back and refer to this particular slide, what you can already see, right, that this is a 7 cross 7 matrix, and when stride equal to 2, your output size is 3. So why don't you go ahead, fill this 7 cross 7 matrix with some numbers, have the 3 cross 3 filter ready with some other numbers, and just perform this multiplication. So it won't take you too much long. So just perform this convolution on your own, right, and maybe refer some blogs also there. So if you are facing some troubles, but try to understand what stride is by writing on pen and paper, right. So once you do that, your check will be this, that your output size should be 3 cross 3. The final activation map size should be 3 cross 3. So that is how your value should come, right. So this is what is meant by stride. So you are basically moving ahead, instead of taking the next immediate next one, you are moving by the number of steps which is equal to the stride mentioned. So if your stride is 3, so your initial position is this. So this cell, you are moving 3 steps from here. So 1, 2, 3, again 1, 2, 3. This is where we faced all the trouble, and yeah, I mean, this is where we said that the code will throw an error. So yeah, I mean, this is not a difficult concept to understand, but a fundamental concept. So in order to, so this is confusing, and even in our initial years we felt a lot of trouble understanding this. So the best way I would suggest is to go write this down on pen and paper, do a little bit of math, and that will clear it out for the rest of your life. So yeah, just do this, and I think it will be much better. So yeah, moving on, we were talking about spatial dimensions. So like how to maintain the spatial dimension. So the point was that I have a 7 cross 7 input, I have a 3 cross 3 filter, right. Now what I why did I introduce this? Because I wanted to have a stride, or I wanted to have a filter size which would basically, how do I put it? So which would basically lead to an integer value in the output size, right? So in order to ensure that, we are putting a what we call padding, right? So this padding will help us make this. So we can set an appropriate padding value so that this output turns out to be an integer, and the everything is good. So this is a cheat sheet. Again, this is suggested by CS231N. So this gives you all the formula in a nutshell. So what you do is, suppose you have an image of size W1 cross H1 cross D1. W1 is width, height and depth. Now there are 4 hyperparameters that are required for the conv. One is the number of filters K. Okay, number of filters, again remember, that is a hyperparameter. So already as mentioned here, the spatial size F, which was 3 cross 3 for us, stride S, which can be 1 or 2 or anything that you want, amount of zero padding P. Okay, so again, like I said, how do you remember what to do? So if your P is 1, your output size will be 7 plus 2 9. So suppose for a generalized P, your output size will always be n plus 2p, right? So if you remember that, in this formula, again let's work it out. So now you have with the padding, your output size was your output size initially was 7, sorry, your input size n was initially 7, you add the 2, so it becomes 7 plus 2 9, 7 plus 2p, where p equal to 1, that becomes 9, 9 minus 3 is 6, 6 by 3, so we faced trouble when the stride was 3, 6 by 3 is 2, 2 plus 1 is 3, so this becomes an integer then, right? And 3 cross 3 is the final output size with that padding value. So now padding, amount of padding that you want is given by this p variable, right? So with this computation, what is the output size that you see? This is what we covered already. So generally we show it for square images, but they have shown it for rectangular images as well. So what is W2 given by? W2 is W1 plus 2p, so that becomes your final image width after adding the padding, minus f by s plus 1. So this is convince yourselves that these are the correct formulas, and what you can do is take arbitrary different sizes of W, H, D, K, F, S, P and just try out and see that these things work. Obviously you cannot take something like 224 cross 224, you have to take something like 7 cross 7, 11 cross 11 to manually verify that this formula indeed works. Similarly for H2, it's H1 plus 2p minus f by s plus 1, right? So you will get used to these formula the more time you spend with. Now the critical, more important thing to remember is that the D2, the depth channel, the number of channels for this particular new image is going to be same as the number of filters that you chose, which is k. Okay, so D2 equal to k. So finally your image becomes W2 into H2 cross k. Okay, D2 equal to k, right? So what we said, we began by saying that these individual filters we are sharing through the entire image. Okay, instead of one neuron having, each neuron having different weights. So with one, so what did we say again? That the kernel size was f cross f, but its third dimension should be same as the depth of the first image, the input image. So we have our kernel finally becomes a matrix of size f cross d1. Okay, so the number of weights, that means, becomes f cross f into d1. Okay, so and now because you have 4 k filters, you multiply this quantity with k, and that makes it f cross d1 cross k weights, and for each filter you have a bias also, so bias term also, so that makes it plus k biases. Okay, so these type of questions may be asked in either this course or other courses that you may take in the future. So keep an eye on these formula. So just have a look at it, it's not difficult to understand. So in the next point is in the output volume, the D depth slice of W2 cross H2 is the result of performing a valid convolution of the Dth filter. So this is the exact example that we gave, that any filter. So if you have a, suppose your output activation map is of size, suppose 30 cross 30 cross 250. Okay, so 250 is your number of channels. Now out of that 250, suppose you pick the 100th one. So the 100th channel that you have, that is the that channel appears because of the convolution. So if your output channel number of channels is 250, then you had basically convoluted with 250 filters, that you have to understand. So you had convoluted with 250 filters, and the 100th channel corresponds to the convolutions that are done with the 100th filter. Okay, so that is what you need to remember. Okay, so we are nearly towards the end of the slides part, but still we need some very important, there are some very important components still left for CNNs. So one is called pooling. Okay, so like I said, the pooling, so you had a, suppose you had a this 6 cross 6 image. So this is 6 cross 6 if it's visible to you, and pooling is a way, pooling operation is a way to downsample the image. Okay, how I want to downsample it is based, is kind of dependent on my requirement, how I want to downsampling means what, I am losing some information. So how I want to preserve the remaining information, so the pooling depends on that. Okay, so what we do here is, so there are two kinds of pooling, one is max pooling, one is average pooling. Okay, so what does max pooling do? Suppose, so when I am downsampling, what does downsampling mean? I will convert this 6 cross 6 image to a smaller dimension, suppose like 3 cross 3. Again the number of channels still remains preserved. Okay, so max pooling does what? Suppose you take this first 3 cross 3 window. Okay, and you take this and you simply take the highest value, okay, which is suppose given by this, you store it here. Okay, and similarly this, right, you take the next one, again you take the highest value, right, you store it here, then you take the last one, okay, and you store it here. Okay, only take the max, right. So that is what is known as max pooling. So you take a window, so all these window sizes, this doesn't have to be 3 cross 3, this will be predefined by you only. So the general norm is to take a 2 cross 2 pooling with stride 2. So once you are well adjusted with these terms, what is the filter size, what is the stride, etc., these will be pretty easy for you to understand. So 2 cross 2 pooling means I will look at a 2 cross 2 window. Stride 2 again means that I will take a jump of two cells basically, and from here this 2 cross 2 that I am pointing at, I will move to this 2 cross 2 that I am now pointing at. Okay, this is the common norm to take stride equal to 2, and pooling the filter size or the window size is also taken to be 2, the path size, right. So what does max pooling signify? That in the window that I am looking at, wherever, so these are all neurons, right. So I am only preserving the max values, that is wherever my filter, wherever it it matched the most with the image. So dot product is like in some sense computing a similarity, right. So wherever the dot product, the convolution returned me the max value, I am only preserving that in a local neighborhood. Okay, so that is known as max pooling. So it kind of like preserves where my filters were most similar to my image. Okay, that kind of information it preserves. Okay, and this is the most commonly used form of pooling. The other is a little bit less common, but again it's still used. What this is called average pooling, and this is again, like the name suggests, all the concepts remain same, the window size, the stride, etc. In a certain window, instead of taking the max, you take the average of the window. right. So instead of taking this particular cell which is suppose the max value, you take this entire window and you average across the 4 numbers, and that is the number that you preserve. So it kind of, average pooling is kind of like you are not retaining the max value here, but you are just trying to make an aggregate, okay, of the window that you are seeing. So in some applications it's good, in some applications it's bad. So if you want to, I mean, what average pooling does is it loses the information of the max value, right. So in that way you can say that max pooling is the more chosen one. So this is all about pooling, which is making sure that you are downsampling your image further. Now once you have, the next step, the last step is that once you have downsampled your image enough, right. So this is what, so you had started with suppose maybe a 20 cross 20 image, and now you have reduced it to 3 cross 3 in this way, right. So 3 cross 3 is much smaller than 20 cross 20, right. Now you can vectorize it, right. So you have this, you can vectorize it, it becomes a finite length vector, I mean something that can fit into the memory, and now you have a fully connected layer on top of it, which will finally lead to your final prediction layer. Okay, suppose you had 4 4 classes in the data set. So you would, in the last layer you would have 4 neurons, which would give you the individual predictions for all those 4 classes, and that is how you arrive at your final class, the prediction, and you can compute the loss function with respect to the ground truth, and you can back propagate and learn all of this. So the learnable component in this entire CNN is this is this kernel that we saw. However many kernels that you have, all are learnable. So they are not Gaussian or any fixed kernels, they are randomly initialized, and you are training them, you are learning them through back propagation. So this is a learnable part, as well as the connections that you see in the fully connected layer. So note that pooling is something that is not involving any training, okay. So there is no learning in pooling, all you are doing is downsampling, you are simply taking some neurons, or you are taking just some average, right. So there is no specific training happening here, so no, it involves no trainable weights. So all the weights that are here are in this part and in these fully connected layers. So finally, I mean, we broke down convolution into many small parts, but this is what a typical model looks like. So the models that we have today, like ResNet, etc., they are much bigger, but yeah, I mean typical convolution layers, if you want to code it up, it may look like this, that you have an image like this, you have one convolution layer, then obviously all of these have to be, so the activation maps that you get, so it's not enough to, so neural networks' main purpose is to add non-linearity to your functions, right. So this non-linearity is what is helping in drawing, I mean otherwise you would have drawn just a like a linear hyperplane that we talked about in the last week. So we do not want to draw a straight line as a decision margin, we want decision boundary, we want non-linearity, right. So always remember that once you get the activation maps after the convolution layer, you need to add this ReLU or some non-linearity to it, to make sure that that power is there, the non-linearity is there. Then maybe you can again add a convolution layer, again a ReLU, then you use a pooling. So at every convolution layer, if you do not use padding, your image sizes go down, right. So suppose if you do not use padding in this particular data set, so in this particular model, by doing this convolution, this image size reduces a little, then again with this convolution it reduces further. Pooling is meant for downsampling, so pooling has further reduced it, but maybe not enough to vectorize it, right. So you go on with these layers, you repeat these layers for multiple times until you have a pooled layer which has a dimension which can be vectorized comfortably, and you can add a fully connected layer on top of it, and then you can make your prediction. So this final so once you vectorize this particular downsampled image, this itself is like a like you can imagine this to be an aggregate vector of the entire image. So it contains an aggregate information of the entire image. So this is a representation that you learnt for the image, right, and this you put in the fully connected layer, and then you make your prediction, and then you go about with the back propagation, right. So this was the last slide that we had. So CNNs are a little bit tougher than back propagation. So it's the sorry, I mean what I meant was that compared to feed forward neural network, CNNs are a little bit difficult to understand, that I agree, and especially with this pooling and so many things going on, back propagating through CNNs is something which is not a very easy thing to do, right. So practice this. So go back and try to work this out and code it up, like how CNNs are getting back propagated every with respect to all these filters. So this is not similar as traditional neural networks. So back propagating through some model like this is still much simpler, but when you have a convolution layer like this, specifically this one, how you back propagate, what are the gradient values, etc., those are non-trivial. So you should go back and find them. What happens when you have a non-zero stride, what happens when you add a padding. So all those things, they require some involved computations, and what happens especially in the pooling layers. So pooling your downsampling, how do you back propagate through that. So all those things are non-linear and non-trivial, and all of you should go back and practice it, so that you are your concepts are completely clear, right. So we also have some code to look at. So this is yeah, so this is some simple code on CNNs. So here, instead of using a simple CNN, instead of using a simple CNN, here we are using a pre-trained model. So like ResNets, which you have heard of, I hope you have heard of it in the previous classes also. So there are, so these architectures that we are seeing here, okay. So this, like I said, is a very simple convolution layer. It's a very simple CNN, but with time people came up with other architectures which are much more bigger, much more like they are much more deeper. Deep is the word that we use. So there are multiple convolution layers which go up to multiple layers, I mean multiple levels, right. So these are called pre-trained models, okay. And because these models are trained on these models are so huge, and they are trained also on huge data sets like ImageNet, people still use them to do some classification or some other tasks, right. So some examples are ResNet, BGG16, etc. So I am not going to, in this code walkthrough, I am not going to go into the nitty-gritties of ResNet or BGG16, but this is just to show you that given such a model, how can we use them and do some train our own model, right. So let's begin with the, so in this import section, so we already looked a little bit at PyTorch, how it looks like, what are the different functions, but yeah, I mean some built-in functions are also available with PyTorch, which are very essential, and you need to use each and every one of them when you train your own model on some data set that you have, right. So okay. So first of all, we import torch, okay. So this sampler, etc. So one thing that you have to make sure, I mean you do not have to do it, but PyTorch will do it for you, is that your training data is shuffled, okay. So like I said last day, that if you have a like training data of zeros of where there are two classes, 0 and 1, the original arrangement of the data can be such that all the 0 classes are together, all the 1 classes are together. So if you train the neural network with such data sets, then the neural network will simply, it will see the zeros first and then the ones. So at the end of the training, it will simply forget what the zeros were, because it saw the 1 later and it only remembered the 1. So that's why sampler or subset random sampler, these sort of functionalities are required so that your training data is sampled, it's shuffled, right. Then Torch Vision is another library where, so Torch Vision has many functionalities. So one out of them is that it stores some of the most important data sets. Okay, so in this particular code walkthrough we are showing an example on the MNIST data set. So MNIST is a very popular data set which consists of handwritten digits. So it's a digit classification task that we do with MNIST. So that MNIST data set is actually present in the datasets module of Torch Vision. Okay, so remember this name Torch Vision, it also stores certain other functionalities, certain pre-trained models like ResNet, VGG16 and so on. Then you have this data loader. So data loader, so kind of one advantage with PyTorch is that it does most of the work for you. Okay, how to shuffle the data set, like shuffling the training data, how to batch them, how to group them into batches, right. All these things are taken care of by different classes or functions defined in the Torch library. So these are things that you have to you have to get used to. Again, subset random sampler we will see in some time. Okay, transforms also, as we go we will see. Again, this is a very useful tool that is very important in deep learning, right. And these are some other libraries that I am not going into at this point because you have seen many of them already. Okay, so this is what is data loading. Data loading is like one keyword that we get in PyTorch or any deep learning modules. So data loading, how to prepare your data, convert it into batches such that you are able to handle it, you are able to train it, right. We train in neural networks, we train through batches, right. So we do not train all the training data at once. So how to prepare the data, pre-processing part, all those things are taken care of by this data loading section. Okay, so this is some function, okay, called unnormalized. This is a class basically where you define mean and a standard deviation. So basically you are normalizing something. Okay, so why it's called unnormalized is beyond me, but you are using it to normalize. Okay, so right, so now like it's written here. So in the function, in the call function, you are taking into consideration this tensor. So this tensor is an image of size C cross H cross W. Again, point to be remembered, in PyTorch conventions are a little bit different. So normally we define an image's dimension to be of H cross W cross C, like H and W don't really matter, but the C part we put in the end in our conventions. But it is not to be forgotten, it's very important to remember that for PyTorch the channel comes first. So that is why it's written in this way. So this is the tensor image of size C cross H cross W that we want to normalize, and this is this is what is, so this is the functionality for the normalization. I am not going into it. So it's t into t times the standard deviation plus m. So cool, so that we are doing, right. So main part, so we are focusing on the main part here, the data loader part. So this function gives you an example of that, right. Get data loaders MNIST. So this tells us that we are dealing with the MNIST data set. So you define a few things here. One is the batch size. So what, in a single batch, how many images do you want, number of workers and all those things will come into. Okay, validation fraction means that how much fraction of the training data do you want in the validation set, and transforms we will just show in a few minutes. Okay, so transforms I don't think they are using, okay, so let me define it here only. So transforms is something, so it's a collection of transformations that you operate. So this transforms is a collection of, or a list of transformations that you do on the image. Okay, the first transformation is always to convert the image, which is suppose NumPy array or some other tool you have used to open the image. So the first transformation is to convert it into a tensor. Okay, that is given by this. Okay, so this is already defined in the library, PyTorch library, right, torch library. So we had loaded this transforms functions from there in the import statements, and all we do is we call the toTensor function of it. Okay, so what this does is, whenever, so this train transforms, whenever you use it to operate on an image, it will convert the image to a tensor. That's it. Okay, so here why I thought of explaining to you in I mean separately is that, so there are other functionalities that you can perform, right. So maybe we will find later in the code base if something like that is there or not. So one other important aspect of neural networks is data augmentation. Okay, so data augmentation, you have limited number of data, so you can augment your training data with some transformations of your original images, right. So you can like rotate your image, you can crop your image, and you can generate different transformations of your original images, and all those transformations you can add to the training data. So that not only increases your number of images, the more data the better, and it also basically makes your model see different angles of the image, which makes the learning better, right. So all these augmentation functionalities that we generally use are also defined in this transforms. So you can have a look at that in you can also look at the PyTorch documentation that I already told you, it's very well written. So what functionalities are there in transforms, you can have a look at that there, right. So you do it for both training and test, right. So now next is you define the data set. Okay, so this data set is MNIST, like I said, and this is defined in the Torch Vision's datasets object. Okay, so Torch Vision, so we had used it in the, we saw it here, right. So this stores all the some of the very important or popular datasets that we use in current deep learning. MNIST is obviously one of them. So if you just do datasets.mnist, it will load the MNIST dataset for you automatically. You do not need to store them on your machine separately, you do not need to download them by yourself, right. And now, so this thing train equal to true, make sure that you are loading the training data. Transform equal to train underscore transform. So this basically converts your downloaded, or sorry, your images, MNIST images, into tensors like we saw. And download equal to true means that I do not have these images on my local system, I need to download them, right. That the download equal to true tells this function that, so it will download it on its own, right, from its own server. Similarly, you have the valid data set and you have the test data set, right. Okay, now basically in this particular loop, it's basically defining the validation set. Okay, so it's saying that if the validation fraction is not given, I'll oh okay, sorry, my bad. So it's saying that if the validation fraction is given, then I'll calculate the number of elements, that number of data points that are allowed for me in the validation set. Suppose out of the 60k images in MNIST, I am saying that only 10k images are allowed in the validation set. So it calculates that number based on the fraction given, and then what it does is it takes the first so it takes from, so that means what, that 50k images are in the training set, 10k images are in the test set, in the validation set, sorry. So your train indices start from 0 to 50,000, right. So your num will be 10,000 like I said, and validation indices will start from 50,000 until the last 60,000, right. So this train sampler, valid sampler, they are basically meant for like randomizing, shuffling your training set and validation set, right. So you define the valid loader and train loader in this way. Okay, so this data loader class is again another very important part. So here you pass the data set that you defined. Okay, you define the data sets here in these three. It's very difficult to remember all of this, so please go through it. So you pass the data set here, the batch size that you defined here. So understand that the data set, okay, this basically downloads the data set for you, or brings them into the memory, right? And the data loader, it basically organizes your data set such that you get shuffled and batched data in every epoch, right? So you define the data set, you define the batch size. Number of workers is actually related to how many workers, how many processes you want to run parallelly, and sampler is given by this. So sampler basically makes sure that your data is shuffled. So you repeat it for the train loader as well, okay, right. And in the else part, it's saying that if the valid fraction is not given, validation fraction is not given, that means that I do not want a validation set, so I only define the training set, train loader, okay. And test loader, remember that for testing we do not need a separate shuffling, we are not using the test set in any way for training. So it's okay if my test set has class zeros in the beginning and class ones in the end. So that's why I directly call this data loader, and I pass the test data and the test data set that I defined above with the batch size, workers, shuffle equal to false, okay, cool, right. So now I return, finally I return the 3 loaders if my validation fraction is defined, otherwise I define the 2 loaders, okay. Similarly, I am not going into this, but there is another data set called CFAR10. So here we have MNIST, right, for this function. Similarly, this function is meant for the data set CFAR10. So it's a data set of images of 10 classes. So they are not digit images anymore, they are scene sort of images, scenery sort of images. So it's a similar thing that they are doing for CFAR10. So here it's they are calling the CFAR10 data set that is stored in the datasets module, right, and the same thing is being done. So again, I think if I remember correctly, the number of images is also same for CFAR10. So it's the same thing, so I am not going into this function, but yeah, I mean you can just go ahead and download CFAR10 and see what it looks like if you already do not know, right. So again, these are some functionalities which we talked about last day, that if you want to, so you are training a model, and deep learning is full of random initializations, right. So very often results depend a lot on how you have initialized your weights, right. So to make sure that when you are running your code in consecutive runs you have the same accuracies, you set these seeds, right. So we talked about all this last day. So you have to set these seeds in this way, and this is something that you have to do every time. Every time you run a PyTorch code, you have to make sure that these are all set, so that you can basically reproduce the results that you get after running the code for one time, okay. Then this compute accuracy function is basically nothing but, so what your model is doing, so it is predicting values, right. It's predicting which class the particular image belongs to, okay. So now you also have a ground truth label, right. So at the end of the training you need to understand, or even during training you need to understand, that whatever your model is predicting, how much of it is correct, that is given by accuracy. Accuracy is what? It's the number of correct predictions divided by the number of correct total examples, sorry, right. So if we go through it, it's something like this, okay. So when you are again one very important point, when you are computing accuracy, it's outside your training module, right. You are not training, you are just evaluating your model, right. So for that you enable something called torch.nograd. When you do this, when you write this statement torch.nograd, it makes sure that PyTorch is not calculating the gradients of your model at all, okay. So it's very important to do this, otherwise you will get different results. So whenever you are evaluating your model, make sure that you do a with torch.nograd. So these are very important points, okay. Then in order to so you initialize 2 variables, correct pred and number of examples, okay. So correct pred will basically denote how many predictions you have made correctly, and number of examples is the total number of examples. So our accuracy will be this by this, this by this. Okay, so this gives you a very first hand example of how you are passing, like you can get access to the data through the data loader, right. So this is how you do it. You write a for loop like this, okay, and yeah, so you write a for loop like this. So what you do is, the data loader, what it has done for you, it has already it has already divided your data into batches, okay. Image, feature, this features basically denotes the actual image, targets denotes the labels, and all of these have been divided into batches. So this I denotes the batch index, okay. So if you have a batch size of 128, this vector, this particular features, this particular image is like a this contains 128 images, okay. So similarly this targets contains 128 classes corresponding to the images, right. So again another important thing, so this, all these signatures you have to keep using, right. So another important thing is that you, because all of this is running on CUDA, so you have to bring everything onto CUDA. So all the tensors that you have in the, that you have defined, that you are using to train the model, they should be all put into the CUDA memory, and that is given by this, right. Device denotes the CUDA memory, and this .to function basically converts your tensor. So it pushes the tensor from the CPU memory to the CUDA memory, right. So now you have this feature and the target, right. What you do is, you have the model, so there is a model defined somewhere. So it's not defined till now, we are just passing it as a parameter to the function. So what we are getting is this, yeah, so this is the model, we are passing the image through it, these are the predictions, right. So we are converting the predictions to it's enough to see what is the, so suppose you are doing a 10 class classification for MNIST, right. So you are as the output of this model, you are seeing 10 values, okay. So these 10 values, whatever is the max of it, that becomes your class, predicted class, right. So it's basically seeing torch.max of logits, comma 1. So this 1 basically, comma 1, this basically so this basically, so this entire thing returns you two things. One is your what is the max value, and second is in which position in that 10 size vector is your max value located, right. So you are taking the predicted labels from the second part, that means you are taking the position instead of the actual max value. So in which dimension in the 10 dimensional vector are you getting the max value, that gives your predicted label, right. So now you add the number of examples to be the target size. So these are all in batches, right. So how do you calculate the total number of examples? So this targets is what, it's a, like I said that it's a if the batch size is 128 and there are 10, so suppose there are 10 classes, so this targets vector is going to be a 128 dimensional vector, where each element denotes the class label of the ith data point in the batch, okay. So like I think we explained this last week, that dot size returns the dimension to you, right. So so dot size returns the dimension to you, right. So this size 0 basically returns the batch size to you, right. So you add num examples, okay, you add to num examples the current batch size, okay, and you go on doing this in every iteration, in every epoch, in every iteration. So and in the correct prediction, you are basically predicting, you are basically seeing that how many number of times is your predicted label equal to the targets, okay, and you are just computing a sum of that. So all these notations you will get used to as you practice more. I know this is very confusing, even I got confused when I learned it for the first time. So this quantity correct pred, okay, this is a sum, divided by number of examples finally gives you the accuracy, and you can multiply it with 100 to get it in percentage. And this is another code for computing confusion matrix. I am not going into this as of now. So, I hope we will resolve the issue of you not being able to access the these codes. So, once you have access to these codes, you can easily look into these functions and you can get for yourself what they are exactly doing. So, how to create a confusion matrix, all of those details you will find in here, right. So, this is the most important part that I wanted to go through. So, we will go through it and like that will end the class. So, right. So, this is the main part. So, this helper function, this is like mentioned here. So, this is helper function for training. So, this is where we train a model. So, at this point I would say that it does not matter that much what the model is. Here actually in this code base is very useful because they are providing you codes for ResNet etc. in this particular code base, but the model can be anything. It can be a CNN model that you have defined on your own, or it can be a neural network as well, but the moral of the story is how to train it, right. You cannot have a model and simply do nothing about it, right. So, in this train model function, first thing that goes is the model, okay. Then number of epochs that you want to train, the train loader. Again we are not calling the data set directly, if you see we are calling the data loader, right. So, train loader, valid loader, test loader, all of them. Optimizer, we have already gone through it. Optimizers like stochastic gradient descent, Adam, RMS prop, all of those. So, whatever is our choice we can put here. So, that optimizer is required. Device, so device is the name of the CUDA memory where you want to load your tensors, okay. Logging interval basically is like when in what interval do you want to print or you want to compute the accuracies, okay. Scheduler is another concept. So, scheduler what it does is, so what it does is, it based on some conditions it modifies the learning rate, okay. So, sometimes it may happen that your learning rate has become too high, right. So, suppose here for example it is written that scheduler on equal to validation accuracy. So, that means what, that if your validation accuracy is dropping, okay, across epochs, after a few epochs the scheduler will make sure that your learning rate has become lower. So, what it means for validation accuracy to be dropping is that your model is kind of overfitting, right. So, then and there if your learning rate is reduced a little bit, you can save your model from further overfitting and you can go to another area in the loss landscape, so that you can reach a better minima, okay. So, so this you can ignore, this is just taking into consideration the time. Then you have mini batch loss list, train accuracy list, valid accuracy list. So, all these are lists because you want to compute them at every epoch or at some intervals multiple times. So, you want to store these loss accuracy values, okay. Most important. Now, training happens in multiple epochs, right. You are looking at the training data multiple number of times, okay. So, for you define the number of epochs from before. So, in the function we had already taken that as a parameter. So, for each epoch so for each epoch we repeat the following. First most important model.train. So, if you do model.train, that tells PyTorch that now you want to train this model, this you have to do, okay, and you will get to know in 2 minutes like why you need to do this again and again, okay. This code you already saw when we were computing the accuracy, right. So, now during training we are only going to use the train loader, right. This is the batch index, this is the image, this is the target. These are some of the usual things that we have already talked about, and what you do is the images that you got, they are naming it features, but these are the images, you pass that through the model and you get the output. Now, the loss is computed on what? It is computed on the output that you get and the target values and the ground truth labels basically, right. So, This is given by this torch.nl.functional.cross entropy. Okay, cross entropy loss is the most common loss that we use for classification, and this is how you define the cross entropy loss. Okay, so again these things you should go back to the PyTorch documentation and have a look at it, and you can also follow this code base because this is very like informative for training neural networks. Okay, so optimizer.zerograd, it makes sure that in the optimizer, suppose you are using stochastic gradient descent, that is SGD, all the gradient values that are there are, they are made 0, right? Otherwise gradients keep accumulating. Again, I mean, all of these points, these are like Bible, so you have to keep doing them. You have to, I mean, you cannot miss any of these points. So when you get access to this notebook, have a look at it and just make sure that next time you write a code you miss nothing out of it. So this should always be there for your reference, right? Okay, most important step, loss.backward. This is what is performing your back propagation operation. Okay, so this is what is calculating your gradients and everything with respect to the loss. And again, maybe this is the most important step actually, where this optimizer.step ensures that your model parameters are updated. Okay, so this completes the back propagation operation for a single batch. Okay, so now next things are very trivial. So you just save the current batch's loss in the mini batch loss list, and you print the whatever epoch you are at or whatever batch you are at or loss you are at, if you want. I mean, these are all trivial details. Next, again another important step is that now you want to, so you can see that this training loop is over, right? So you have trained the model for one epoch, and now you want to see what is your validation or test accuracy or even training accuracy, right? Again, don't ever forget to put this. Okay, so this model.eval will tell your model that now you are in the evaluation mode. Okay, you want to evaluate, right? And again, when you are evaluating, do not forget to put this torch.nograd. So nograd will ensure that torch is not computing any gradient for you, right? So that will save a lot of memory. Otherwise, during back propagation, torch has, if you don't tell torch to not compute gradients, it will compute the gradients, and that will take up a lot of memory. So just remember to switch this on, right? Then you compute the train accuracy and validation accuracy, right? So these are again some print statements which are trivial details which I am not going into. Okay, right. Now when you suppose if the scheduler is not none, so whatever scheduler you define, you can look into those things, what are the good schedulers, etc. So just one thing, that if the scheduler on variable is equal to validation accuracy, then your scheduler will depend on how good your validation accuracy is. Is it increasing or is it decreasing? Otherwise, some people also use mini batch loss, the loss that you incur in order to set the scheduler, right? This finally completes our training, right? So you can see that we have gone through all the epochs. We have always like for the entire training set we have trained the model, and then finally we are, by making model.eval and torch.nograd, we are evaluating the training and validation accuracies for the model, right? Finally, once the training is over, this is the final step, right? So you now compute accuracy on the trained model over the test loader. Okay, so this gives you your final accuracy. This is the last thing that you want. Okay, so again these are some helper functions which you can go through, right? So these are helpful in plotting your results, and I am not going to go through the next part. So we are already almost our time is also over. So these parts you should look at yourself. And yeah, this is what I was talking about actually when I said that these transforms functions, that are present in torch vision. So they give you the opportunity to augment your data set in many ways. So there are many functionalities like resizing. So you can resize your image to a specific, suppose your training data consists of images that are all of different sizes, so you can resize them to the same size. You can do random crops on them. So these are all data augmentation methods, right? You can even normalize them on all three channels. Okay, so this is what I wanted to show. So below you have examples. So the above example was for the MNIST data set, or it was a simple simple description of how a training module looks like. I feel that that is the more important part for you to know. So here you can see that in this section, which I am not going through, so they are basically showing you how to train a ResNet 34 model on CFAR 10 dataset, and so they have defined the model below. So this is the entire ResNet model. So if you since you are aware of it, you can have a look at it. It's fresh in your memory, so before you forget, you can just go through this code and understand, like I mean, whatever you have learned, try to match it up with the code that is there, and it just trains the model using the training script that we saw, right? And then it yeah, after the training, this is the final accuracy that we get. Similarly, there are other, so yeah, so these are some results on the CFAR 10 dataset. So again, I'm not going into this and keeping this as a homework for you, because I mean, what we have covered today itself is a lot. So I believe that going through ResNet at this point will not really help you that much. So best thing is to get used to with the top part. The more important, the very small concepts in PyTorch that you want to learn, and you want to, so that you are able to train a model. So first understand how to train a model, and then slowly you will also you can also do hands-on on the ResNet code that is provided. Cool. So with this, I think we can end the call for today, and we'll meet again next week. Okay, somebody, I think the person already left. Okay, I'll maybe answer the questions later. Thank you, everyone.